Let's now consider a dipole that is placed in an external field, E bar, so an external electric field. We assume that it's a permanent dipole and it exists without the field and does not break apart in this external field. Okay, so we can determine the torque about the midpoint between these two charges in this dipole. So if we have a negative charge and a positive charge, we are going to find the torque about here, okay, about this point here. Now remember how we can determine torque. Torque is equal to R cross the force between the two points. So R cross F. Let's see if I can draw it. Torque is equal to, R cross F. Now we did look at torque when we were talking about, let's see, we were talking about torque of rotating objects. So that was last semester in the first series of physics. And so we didn't really look at it in terms of cross product or anything, but we did note that it was the cross product. And so we can talk a little bit more about that in general, but let's for now just take this equation here, torque is equal to R cross F, and put it in the scenario that we have here. We have two charges with some force, and the midpoint between the two is going to be our distance, R. So we now have our distance between the two charges divided by 2 would give us this distance here, which is what we're concerned with. And we will cross that with each of our forces. So we have this force here, which is a positive force for the positive Q charge here. And we will add that to our other one here. We have a negative Q charge and our force negative as well. Okay, so we will then note that force is going to equal Q times our electric field, right? We looked at that earlier. So we plug those guys in. The positive will be positive. The negative will have a negative out front for the charge. And then when we do that, we can combine the two and get one solid equation here, Q D bar cross E bar, or the distance vector between the two charges of Q, since they have the same charge, and crossed with the electric field, that net external field. We will define the dipole moment of the dipole, which is going to be represented with a P, and this just is defined as Q times D, that distance between the two charges. And therefore, our torque can be written as P cross E. Okay, so again, this shows a dipole in an external field. The net force on the dipole is 0, right? Because we have two charges that are opposite each other, but the torque is not 0. So because the torque is not 0, then we will get a rotation within these dipoles. So the dipole will rotate and it becomes aligned with the external field. And so this is what we have here and here, just showing that. And this is also showing our P, or our dipole moment, along with our displacement here. Okay. All right, our displacement vector, I should say. So again, when we have these dipoles, we will have a torque involved. So these dipoles are going to rotate. Okay. So we can induce dipoles. So let's, for example, take this neutral atom here, and we will induce a dipole by an external electric field. So we introduce an external electric field, E, and the dipole moment will be induced, and it aligns with the external field, like we just saw. Okay, very similar. We should also note that the total electric field would equal the external electric field plus the dipole electric field. So we would get this equation down here, and just in any case that we want to maybe determine the external field or the dipole field or the total field, determining either of those if we're given a couple of the other information that we would need. Okay? All right, so that's the end of this section. Next time we'll start to talk about electric flux and then Gauss's law, and then conductors in electrostatic equilibrium. Let me know if you guys have any questions as always, and we will look at some examples in person.